For this lab, we measured and simulated the magnetic field of a bar magnet. Using a phone to measure the magnetic field produced, and a meter stick to measure the distance from the magnet at various values for magnetic field, I was able to measure the data that you see here. Before my measurements, I ensured that the magnetometer was facing north so that it would have a near zero magnetic field in the x direction when it was far away from the magnet. During my measurements, I observed that as the distance between the magnetometer and the magnet decreased, the value of the x component of the magnetic field increased or decreased depending on which way the magnet was flipped. However, regardless of which way the magnet was flipped, the absolute value of the x component always increased as the magnet and magnetometer moved closer to each other. You can see this very clearly here when we have just very clearly the distance, as it increases, the magnetic field decreases, and as the distance decreases, the magnetic field increases. Now, moving on more towards the coding portion of my lab, in order to model the situation, I needed to implement this equation right here for the magnetic field. From the data I've already collected, we have this magnetic constant, we have the value of R, and we can easily get the value of R hat. But we're missing mu. And luckily, we can find it using the trend line that you can see right here for this logarithmic graph of the data for log of the magnetic field versus the log of the distance. And as you can see, the slope is the distance dependence here. So this is the equation for the trend line. And the slope is the distance dependence. And the intercept is the natural log of this value right here, k. And from the natural log of k, we can easily get the value of k. And I've calculated that and written it here. And as you can already see from this equation, right here, we can solve for the value of mu. All we need is this constant and 2. Just divide by both of those, and we have the value of mu. And if we go to my code, you can see that I have done that right here. And the value comes out to be this 4.375. And now we can implement this equation, which I've done right here, to find the value of the magnetic field at various positions. And as you can see, I have done various positions that are 0.1 meters away. And we have a few that are on axis and a few that are perpendicular. And if we run the program, you will see that the ones that are on axis seem to be roughly twice as large as the ones that are perpendicular, which lines up exactly with our equation and what we would expect to see for perpendicular versus on axis. And so now we can go on to discuss the experiment for when the magnetometer is along the 45-degree axis from the magnet. And here are my numbers from the experimental data. So this is the off axis, the 45 degrees. And as you can see, I had to account for the magnetic field due to Earth in the y direction right here. And if we go back to our model of the situation, you can see it represented by this magenta arrow right up here. It's a bit off from the rest of it. And you can also see at the bottom calculated the calculating magnetic field at this position. But what's very quickly noticeable, especially by this z value right here, by this z component, is that this doesn't line up almost at all to our observed data. I mean, the x value lines up quite a bit, and the overall magnitude of this is going to line up somewhat. But it's very obvious that, I mean, in our observed data, the z component simply isn't 0. And there's a few potential reasons for this. One big reason for this is that the magnetic field due to Earth is not accounted for in our model. And another reason would be the fact that everything in our model is treated as a single point in space, while these are all just treated as the magnetic field at these positions, the magnetic field being exerted from this position, While in the real world, our magnet and magnetometer are 3D objects, so they might not be perfectly aligned in this XY axis. And so that's all of the data experimentation and modeling for this lab. But there's a few key things that we need to discuss before we're quite finished with this lab. First is the fact that I oriented my magnetometer to compensate for magnetic north and zero out the x component of the Earth's magnetic field. This was absolutely necessary because in the case where I don't do so and instead measure at some random angle, each of my data points would be skewed by whatever the value of the x component of the Earth's magnetic field is at that angle. Another thing we'd have to consider is what would happen if we stuck two magnets together end to end and ran the experiment again. Well, the two magnets together would essentially act as one combined magnet that creates a greater magnetic field, so the distance would need to be greater to measure the same values for magnetic field. I tested the situation on my own a bit, just in case, and of course, the results prove the physics. Thank you for watching my lab.